Hi everybody, welcome to Tuesday's class for Chem 103. This is Module 3, and today we're going to be talking about ions and ionic compounds. Oops, I guess I should fix my title here. Ions, there we go. So this week we're doing some labs regarding ions. The ICP sadly is not working, so we're going to have to hold off to run those scans, but we can make our samples and we can talk about the minerals. Some of you did that yesterday, some of you will be doing it tomorrow. Those all involve ions. So last module we looked at what we called covalent compounds, which are these compounds where atoms are connected by sharing electrons. And so this time, we're going to look at the other class of compounds, which are called ionic compounds. Now, ions are just simply charged particles. So some common ones are something like Na+, so a sodium ion, is a sodium atom that has lost an electron. So if we go back a couple modules now, if we think about a sodium ion, or a sodium atom, we look at the periodic table and we can know that it has 11 protons, some number of neutrons depending on what isotope it is, and then 11 electrons in the neutral atom. But for sodium ion, we still have 11 protons because we know the number of protons defines what kind of an atom it is. But this time we've got 10 electrons. So with one fewer electron, we now have what we call an ion, which is a charged particle. It has a positive charge, and so it's going to act like any other charged particle. It's going to be attracted to negative charges. It's going to repel other positive charges, stuff like that. It can move around to carry a current. This can also happen in the other direction. So you can have a chlorine atom that has 17 protons and 17 electrons. And you can have a chloride ion that has 17 protons and 18 electrons. So you add an electron, and then you end up with an ion or a charged particle. And then this can happen with multiples as well. So you can have, with multiple electrons, so you can have an oxygen atom that has 8 protons and 8 electrons. And you can have an oxide ion that has 8 protons and 10 electrons. So gaining electrons is going to increase the amount of negative charge. Losing electrons is going to increase the amount of positive charge. Okay, now why does this happen? Why would atoms even do this? Why aren't they just neutral? The reason is that most of these atoms, at least the ones that we're going to look at, are more stable, more energetically stable in their charged form than in their neutral form. So for example, sodium as a neutral atom is an extremely reactive metal. You can look up videos of people putting sodium in water. You can see that it fizzes and it actually creates hydrogen gas. It's very reactive. Sodium ion, the thing over on the left, is the sodium that's in our food, that's in salt, that's in our bodies, that it's important for our nerves to work properly, so necessary for life and important. And the same thing with chloride. So chlorine, the neutral atom, actually doesn't exist as individual atoms like that. Usually it's Cl2, but that's chlorine, which is a gas, a poisonous gas. Greenish. And then chloride is the ion that's part of sodium chloride, that's in salt. So you'll notice some ions change their name when they go from the atom to the ion. Chlorine is the molecular or the atomic compound, and chloride is the ionic version. But sodium doesn't do that. So this is sodium, the metal, and this is sodium, the ion, which maybe we'll write ion just to make that more clear, but it actually would just be called sodium. It wouldn't necessarily have that ion word next to it. So these positively charged ions generally don't change their name. The negatively charged ones do. And then speaking of names, we have two categories of ions that we can talk about. We have cations, which are positively charged. And we have anions, that are negatively charged. All right, so cations and anions. So from now on, when we talk about positively charged atoms or ions, we're going to call them cations. When we talk about negatively charged ions, we're going to call them anions. Okay, so that's kind of the basics. The first part should have been review from the activity you did in the previous module about atoms. If this seemed new to you or you didn't know how to do those counts, please go back and review that because that's necessary to be able to find these ions. Okay. Next we're going to talk about common ions. On the periodic table. I don't have a periodic table on this device, so I'm just going to draw one. I'm not going to write in all the things, but if you have some sort of a notebook or something where you can look up the periodic table, or online, just open a browser and put in periodic table. We're just going to look at some regions of the periodic table. So there's our basic shape. We've got hydrogen over here. We've got helium over here. Well, I'll just put in the corners here, francium and radon. There are some new ones below here now. I guess radon would technically be up a little bit higher because there's a new one under here now. But anyway, and we'll just ignore the lanthanides and actinides for now. So it turns out that depending on where an atom is in the periodic table, sometimes you can predict what kind of ion it likes to make, and sometimes you can't. So the ones where you can, I'm going to highlight here. So first we've got the first column and the second column. All right, so first column, ions are always +1. So everything that you see in that first column of the periodic table, hydrogen, lithium, sodium, potassium, rubidium, cesium, makes a +1 ion. Move over, and we've got a +2. So that's a pretty easy pattern to start with. You start with +1 and then +2. So that means anytime you see somebody talking about a calcium ion, calcium is Ca, it's in that second column, it's number 20, element number 20. You know, or you can know now, that that ion is going to be calcium +2. And that's true for anything in that column is always going to be +2. Anything in the column to the left of it is always going to be +1. All right, so this is helpful to us because we can know that there are going to be some ions that always have that particular charge. All right, so then we're going to skip this middle area here because that area does not have predictable charges. Many of those atoms can make different charges, like iron, for instance, Fe, which is right around here, can be either +2 or +3. Copper, which is over here, can be +1 or +2. So a lot of those have different possible ions. So there's no just automatic, we know that this is going to be a particular ion. So we'll talk about that in a minute when we get to those. And then some of these nonmetals over here also don't have predictable charges. But when we get over to the very last column here, so that's going to be the one that has fluorine at the top. Those are all -1. We're going to ignore the noble gases for now because they don't generally make ions. So that's going to be our -1. And then a similar pattern kind of repeats itself for a while, where we can go -2 for the oxygen column and then -3 for the nitrogen column. But you'll notice I'm cutting it off a little bit because that kind of breaks down as we get into the lower parts of those rows. All right, there are a few other ones around that always have the same, like aluminum is always +3, zinc is always +2. You don't necessarily always have to memorize these, but the way that we're going to talk about naming these ionic compounds relies on knowing some of these patterns and understanding that some of these are going to have that we can predict their charges, predictable charges. That's what I was trying to say. All right, so we use this when it comes to trying to figure out a formula from the name of the compound. Right, so let's say you're reading a procedure and it talks about a particular compound, let's say calcium chloride. Okay. Now that's a fine name, but you're going to be writing in your notebook and you want to know the chemical formula for calcium chloride. You could look it up, but if you know a couple of the things that we've just been talking about, we can actually predict this compound. And the way that we do that is we first write down the ions that are involved. So we've got calcium and we've got chloride, and we make sure also to note their charges. So looking at the periodic table, we know that calcium is in column 2, so that one's going to have a +2 charge. Chloride is in column 17 or 7A, so that's going to have a -1 charge. And then we can look at those ions and we can think, all right, if we need a neutral compound overall, how many of each ion do we need? And the answer is that we would need 2 chlorides to balance out the calcium, because calcium is +2, chloride is -1, so we need 2 of these to make -2 to balance the +2. So that means that our final formula, taking all of that into account, is going to be CaCl2. All right, let's try another one. Sodium fluoride. Same procedure. We write down our symbols. Then we figure out the charges. We can do that again from the periodic table. We know sodium is in column 1, so that's going to be +1. Fluoride is in same column as chlorine, so that's going to be -1. So we've got +1, -1. We don't have to adjust those numbers at all. That just becomes NaF. All right. So that's our formula there. Sometimes these can get a little bit trickier. So for example, aluminum oxide. Aluminum is one of these special ones here that is not in a regular column that has predictive charges, but aluminum is always +3. And oxygen is always -2, or oxide is -2. So if we wanted to build that into a compound, we need to do a little bit more than just changing one. So for example, I've got 3+ and 2-. If I add another oxygen, now I've got a total of 3+ and 4-. So that still isn't balanced. I can add another aluminum. Now I've got 6+ and 4-, still not balanced. Now I can add another, oh no, my lights went off. Another oxygen, now I've got 6+ and 6-. Let me finish this up and then I'll go turn the lights back on. And so that compound, now it's finally balanced, is going to be Al2O3. And if you've looked up in some of the other materials, you might see some shortcuts there to help you with that if you read some of the sections that were recommended. All right, I'm going to turn the lights on. I'll be right back. Okay. All right, so that's how to build a basic compound, a basic ionic compound from the names. Notice that the names don't use the prefixes that we sometimes see in other types of compounds. So like calcium chloride isn't called calcium dichloride, even though there's 2 chlorines in there. And that's because the charges are predictable, so we know there has to be 2 chlorides to balance out the calcium. The calcium's +2, the chloride's -1. There has to be 2 of those chlorides to balance out that calcium. All right, so the next thing then is, what about all of those other elements in the middle here that we didn't talk about? How do we deal with those compounds? So we might call that when a charge is not predictable. And this really only applies to cations. The anions are either going to have always predictable charges from the periodic table, or there's some other thing that we're not even going to deal with. But these types of compounds actually have to tell you what the charge is. So I mentioned earlier that iron can be +2 or +3. In order to know which one we're talking about, we have to actually say, is this iron +2 or iron +3? And so there's a Roman numeral in parentheses after the name, and that tells you the charge. All right? So iron 3 chloride is going to tell us that we're dealing with this ion Fe3+. Notice how it applies to the charge, not the subscript. Everybody always wants that number to mean subscript, to mean it's going to be like Fe with a little 3 at the bottom, but that's not how it works. It depends what kind of ion it's paired up with, what the subscript numbers are going to be. So first we find the ions, and then we put them together and balance the charges. Chloride is the same as we've always seen, so it's -1. So we've got Fe +3, Cl -1. So we're going to need 2 more of these, 3 total, to make 3- to balance out the 3+ on iron. So that formula is going to be FeCl3. All right, see that? See how that works? Okay. Give this one a try on your own. Copper 1 oxide, and see how you do. Pause the video if you're watching later, so you can give this one a try. Otherwise, just come back to it afterwards. All right, the last category of ionic compounds that we're going to talk about are the polyatomic ions. So these are ions that are made out of more than one atom. Notice all the ions we've talked about so far are just one atom. So we take one atom cation and one atom anion and make a compound. But there's also lots of ions that are made up of multiple atoms. And so I'll give you a few common ones here. There's nitrate, which is NO3-. There's nitrite, which is NO2-. Carbonate, phosphate, sulfate. There's lots and lots of these. You can look up a table of polyatomic ions and see a bunch of them. In a regular general chemistry class, you would have to memorize all of these. In our class, I don't think that's really necessary. You can look up the ones that you need to look up. But the key here is there's no magic formula from the periodic table to figure these out. You just have to know or look up that nitrate is NO3, nitrite is NO2, carbonate's CO3, and then these are the charges that they have. So it's just kind of like a thing you have to memorize with flashcards if you want to know them all, or you look them up on the table. But what I want you to be able to do is recognize when a name indicates a polyatomic ion and that it's something that you have to then look up. So if you see a compound name like sodium sulfate, recognize that sulfate is not just S. Just S would be sulfide. All those monoatomic ions end in "ide." So the fact that it's sulfate, that it ends in a different ending, means, aha, this is polyatomic. I have to go look this up and figure out what this is. Or maybe you just know it, I don't know. So I look it up on my table and I see that sulfate is SO4 2-. I use the same strategies that we just talked about earlier to find sodium. And now I can put these together in a compound the same way. So I can recognize that I need 2 sodium atoms to balance out that sulfate. So I've got Na2SO4. And that's my compound. I can also have multiple of these, multiples of the polyatomic ions themselves. So I can have something like calcium phosphate. Calcium, of course, is Ca, and now we know that we can look it up on the periodic table and figure out that it's 2 plus or plus 2. That's interchangeable, by the way. You can write it as 2 plus or plus 2, doesn't matter. And then phosphate, we recognize that's not just P. That's a different thing. That's this polyatomic ion. So we're going to look that up on our table of polyatomic ions and figure out that it is PO4 3-. So now we have to balance this. This is the same kind of balancing that we did up here with aluminum and oxide, or similar, so that we've got, we kind of have to go back and forth until we find the same charge for positive and negative, the same overall positive and negative charge, so that it's 0 overall. Which is going to happen when there's 3 of the plus 2 and 2 of the minus 3. So the way we write this compound then is Ca3PO4 2. And we use parentheses around the polyatomic ion to indicate there's more than one of that whole thing. Notice when there was just one of them, we left the parentheses out here in sulfate. So that doesn't need parentheses, but down here in phosphate we do. There are also positively charged polyatomic ions. I didn't put any on here, but a common one is ammonium. So again, if you see that word ammonium, you can try to look it up on the periodic table, but it's not there. And that should be a clue that it's something else. It's this polyatomic ion that you have to look up. There are a couple that are sometimes throw people off here that I'll note here. Hydroxide, which we used in the biodiesel synthesis last week. Whoops. Hydroxide is a polyatomic ion with formula OH and charge of -1, but it ends in "ide," so it kind of sounds like it should be on the periodic table. You can recognize that it's not because there's no hydroxygen or something like that, hydroxo whatever, that's on the periodic table. There's hydrogen, there's oxygen, but there's no hydrox anything. So that's a polyatomic ion. And then another one that ends in "ide" is cyanide, which is Cn, also with a -1 charge. And again, that ends in "ide," but it's not on the periodic table. There's no cyano whatever on the periodic table, and so that is not going to be a monoatomic ion. That's going to be polyatomic. All right, so that's the basics of ions and ionic compounds. You should be able to do the things that we just did together. You can look up polyatomic ions, but if I give you a name in any of these formats, assuming you can look up the polyatomic ions, you should be able to write the formula. Notice I'm not asking you to go the other way around. It's maybe a little bit trickier to take the formula and give it the correct name always. So don't worry too much about that. But you should know that, first of all, ions are different, have different chemical properties from the neutral atoms. And when they form ionic compounds, these are the types of things that we're talking about. The reason that ionic compounds are set up like this, and we don't use lines, like we don't say, where's our example here? Like, okay, let's look at NaF. We don't ever draw NaF as Na with a line to F. We don't do that because that line has a specific meaning in chemistry, and it means that there are 2 shared electrons between those 2 atoms. In an ionic bond, that's not really happening. All that's happening here is the negative and positive ion are associating with each other because there's an attractive force between negative and positive. So they're not specifically connected in the way that a covalent bond connects 2 atoms. They're just attracted to each other based on their charges. And so in the solid state, they pack together positive and negative ions close together because of that attraction. But for example, when you dissolve an ionic compound in water, the ions actually split apart and water surrounds each ion, the positive ion and the negative ion. They no longer are really associated with each other. They're separate in solution. Whereas a covalent compound, with some exceptions, generally when it dissolves in water, if we think about something like sugar, sucrose, nothing breaks apart. The atoms are still connected together in the same way that we would draw the structure. They just all become solvated with water. So water molecules surround each molecule of sucrose. Ionic compounds actually break apart. And that's why ionic solutions conduct electricity and solutions of covalent compounds generally don't. So sometimes ions in solution are known as electrolytes because of the way that they can conduct electricity. All right. Let me know if you have any questions on these. Tomorrow we're going to talk about going back to organic structures and talking about our biodiesel synthesis and our biodiesel reactions of hydrolysis and condensation. So look for that tomorrow at 1 o'clock over in room Z351 if you're here on campus, otherwise online same time. So I'll see you then. Bye everybody.